Welcome to This Explainer. Today we are going to untangle the wild, sometimes messy world of modern software authorization. You know, we all understand how critical security is to software development, but today we're looking at the hidden engine that actually decides who can do what inside your complex systems. And look, when this engine breaks, you don't just get a minor software glitch, you get front-page news. We're talking massive data breaches, catastrophic compliance fines, and a total loss of customer trust. Getting this right is absolutely fundamental to any modern architecture, and yet it's honestly one of the most consistently misunderstood aspects of system design. Think about it this way. Authentication is locking your front door. It verifies who someone is, checks their ID, and keeps strangers out on the street. It answers one simple question: are you who you say you are? But authorization, that is the critical and usually much more complex step of deciding who is actually allowed to open the fridge once they're already inside the house. Because just because someone is allowed in the building doesn't mean they should have access to your most sensitive, confidential data, or, be allowed to rearrange the furniture. If you throw a house party, you authenticate people at the door to make sure they were actually invited. But your authorization rules dictate that guests can use the guest bathroom, but absolutely nobody is allowed into your master bedroom. In software, this distinction is literally a matter of life and death for your data.
Okay, here's our agenda for this explainer. First, Section 1, Beyond the Locked Front Door. Then Section 2, RBAC, Role-Based Access. Section 3, ABAC, Attribute-Based Access. Section 4, ReBAC, Relationship-Based Access. Then we'll tackle Section 5, Scaling to Microservices, and finish up with Section 6, Choosing the Right Strategy. We're going to methodically scale up the complexity of access control so you can see exactly how these systems evolve.
Section 1. Beyond the Locked Front Door. To really grasp what's beyond that door, we have to recognize that modern systems aren't just one monolithic application sitting on a single server anymore. If they were, this would be incredibly easy. But today, they're a sprawling, chaotic jungle of microservices, third-party APIs, and serverless functions. And every single one of those endpoints needs to constantly ask the exact same question millions of times a second. What is the specific user allowed to do right now? Well, we've got a visual roadmap here showing the 3 core models to solve this. They all tackle the exact same problem, but in completely distinct, philosophically different ways. You grant access based on a static badge for RBAC, specific dynamic conditions for ABAC, or strictly based on who you know for ReBAC. Moving from one to the next isn't just about using fancier tech, it's a direct response to the massive complexity of how modern businesses actually operate.
Section 2, RBAC, Role-Based Access.
Let's start with the absolute simplest and most common model out there. If you've ever built a basic app, you've probably implemented some flavor of this. Think of a role as a bucket. In RBAC, instead of handing out 50 individual, highly granular permissions to a brand new hire on their first day, which, let's be honest, would take forever and inevitably lead to mistakes, you just drop that user into the manager bucket, and they instantly inherit everything they need. A permission is simply the specific action they're allowed to take: reading a quarterly report, deleting a stale invoice, approving a refund. The real elegance of RBAC is in this grouping, because it perfectly mirrors how HR departments actually think about jobs.
Notice how cleanly users automatically inherit all the permissions attached to their assigned role. The manager role automatically grants access to read documents, change them, and validate those changes. You don't have to assign those 3 permissions individually to every single manager in your company. This makes initial system setups incredibly fast. Onboarding a new employee is a breeze. When someone gets promoted, you just swap their role from user to manager, and the underlying permissions seamlessly adjust. For a small startup, this mathematical simplicity is absolutely beautiful.
But as an organization grows from a scrappy startup into a massive enterprise, you start falling into a dangerous trap. You begin creating highly specific roles because those simple buckets, they just aren't enough anymore. First, it's just admin, but then the finance team says, hey, we need an invoice_admin. Then the European office says they need an invoice_contract_admin_EU. Until suddenly, you have 1,000 users and 3,000 highly specific roles. The list becomes completely impossible to manage, audit, or even understand. If a compliance officer asks you exactly what Role 732 legacy does, literally nobody knows. This is the dreaded role explosion, and it inevitably happens when you try to cover highly dynamic access needs with rigid static roles.
Section 3, ABAC, Attribute-Based Access.
When static roles fail to capture real-time context and your role lists are exploding out of control, we have to evolve. ABAC completely ditches basic roles and instead evaluates dynamic attributes using a policy engine. It evaluates rules conceptually like, if this and that, then allow. It answers complex questions like, is it working hours right now, or does the user's department explicitly match the document's assigned department? An attribute is simply a piece of metadata. It could be about the user, like their security clearance. It could be about the resource itself, like its sensitivity classification. Or it could be about the environment, like the IP address or the time of day. For example, a high-security hospital might use ABAC so that a doctor can only access a patient's medical records if they are currently clocked in on shift, an environment attribute, and the patient is currently assigned to their specific ward, a resource attribute.
So the crucial point here is how this plays out in practice. Mary and John get access to sensitive documents because their specific attributes meet the rigid policy criteria enforced by the system. Mary has top-secret clearance, and John is located in the U.S. region. Bob, however, lacking both the top clearance and the correct geographic region, is completely shut out. He doesn't even know the documents exist. This model brilliantly enforces the principle of least privilege, ensuring users have the absolute minimum access they need based exactly on live context. You don't have to manually remove Bob's access when he travels outside the U.S. The system evaluates his location attribute in real time and just revokes it automatically.
Section 4. ReBAC, Relationship-Based Access.
But what if access shouldn't depend on generic job titles, and it shouldn't even depend on dynamic attributes? What if it should depend on how people and resources are explicitly connected to one another in the real world? Enter ReBAC. In this model, access relies entirely on a vast web of connections. The system maps out a literal graph of entities. It looks at nodes, like users, documents, or teams, and it evaluates the edges or relationships between them. It asks, does user A have a direct line to document B because they created it? Or are they part of a group that has a line to document B? We ask if someone owns a file, or if they are part of a specific team that was explicitly granted access. It is a completely different way of mapping human intent into software logic.
This model is the absolute powerhouse behind dynamic, modern platforms like Google Docs or GitHub, where relationships like ownership, explicit sharing, and nested team membership drive every single access decision. It's not about being an admin of Google Docs. It's about whether you were explicitly invited to view that specific spreadsheet via an email link, or if you manage the person who created it. The graph actually understands the corporate hierarchy. It can traverse relationships to figure out that because Sarah manages David and David owns the project file, Sarah inherently has read access to the project file. It grants access dynamically based on those exact human-defined relationships, which is just incredibly powerful for collaboration.
Section 5. Scaling to Microservices.
Now, those three models are pretty cozy and straightforward to build in a simple monolith, where all your business logic, your user data, and your permissions live in the exact same process and query the exact same database. But as we shift to the dangerous distributed architecture of microservices, enforcing these rules gets infinitely more complicated because your data is scattered across dozens of different servers. This necessitates a strictly enforced zero-trust environment. In a distributed system, if one service just blindly trusts an upstream services authorization check, a single mistake compromises the whole chain. If the billing service assumes the web gateway already checked permissions, an attacker who bypasses the gateway suddenly has the keys to the kingdom. Every single microservice must validate access itself. And crucially, all teams must have a shared vocabulary. If the shipping service thinks the region attribute means a two-letter country code and the tax service thinks it means a massive continent, your access rules will break unpredictably, leading to massive security holes.
Implementing ReBAC in a microservices architecture is particularly challenging. Because no single microservice knows the whole user relationship graph, architectures often require a central relationship store to maintain the bigger picture, similar to how Google built their famous Zanzibar system. Individual services like invoice, order, and payments can no longer make decisions in isolation. Instead, they have to continuously sync their local relationship data to this one central brain. They are constantly whispering to the central store, hey, user A just created invoice B, or user C was just added to the payments team. This keeps the central graph updated in real time.
When the payment service needs to make a critical authorization decision, it can't just check its own local database. It simply fires off a query over the network to the central store to confirm if user Joe truly owns the invoices in question. The central store, functioning like a highly specialized, lightning-fast graph database, evaluates the relationships, traversing the graph in real time to check for nested group memberships or direct ownership. It then returns a simple yes or no. This beautifully keeps complex authorization logic out of your individual microservices, keeping them lightweight and focused purely on business logic.
But this introduces a terrifying architectural risk. If that central store goes down, if it literally or figuratively catches fire due to a bad deployment, a network partition, or a massive traffic spike, your entire system goes dark. Even if your order and payment microservices are perfectly healthy and running smoothly, they can't verify access for a single user request. They have to fail close to remain secure, which brings your entire application to a grinding halt. That central brain becomes a massive, system-wide single point of failure.
You could try an alternative to avoid that single point of failure. You can embed relationship and role data directly into the user's identity token, like a JWT, often called a FAT token. This avoids central queries entirely because the microservice just reads the token the user hands it. That gives you a huge performance boost and completely eliminates that single point of failure. But beware, that trades architectural safety for the severe risk of using stale, incomplete, or forged data. If a disgruntled employee is fired and removed from a team, but their JWT token doesn't expire for another hour, they have a 60-minute window where they can still access highly restricted data. The microservices are happily accepting the token because they aren't checking the central database anymore to see if the user was recently terminated. It's a really harsh trade-off between absolute availability and absolute security.
Section 6. Choosing the right strategy. Now that we've seen how to implement these in both safe monoliths and treacherous microservices, how do we actually choose? Well, here's your ultimate cheat sheet to guide your architecture. Use RBAC for simplicity in smaller internal apps, but remain vigilant about role explosion. Turn to ABAC for context-heavy, heavily regulated systems where things like time, location, and clearance level dictate access. They'll be prepared to manage complex policy definitions. And deploy ReBAC for modern collaboration tools where sharing is paramount, accepting the technical challenge of graph complexity and database traversal. Ultimately, the absolute best systems use a hybrid approach, perhaps using RBAC for coarse-grained basic app access and ReBAC for fine-grained document sharing once the user is actually inside.
So I want to leave you with a provocative thought. Think about your current software architecture right now, today. Are you relying on an exploding list of outdated roles that nobody understands anymore? Or is it time to start defining exactly who has the right to open your fridge? Because the security, scalability, and compliance of your entire system depends entirely on your answer to that question. Thanks for joining me on this explainer, and I genuinely hope this deep dive helps you build safer, smarter, and more robust systems.